Hi, and welcome to week 7. I thought we'd try something new with a video and audio podcast this week. Let's start with a ping pong ball conundrum. First, we have to summarize the key facts. The experiment lasts exactly 1 minute, but when you cut time in half, the exercise of putting ping pong balls in and taking them out never ends. So, if you look in the barrel and you're thinking if there's some balls in or some balls out, let's see if you could name one. Name one ping pong ball still in the barrel. As we look at this Excel spreadsheet that I built, you can see how if each time 10 balls go in, I pulled one ping pong ball out. For example, this is when I pulled ping pong ball number 13 out. If I had the time and a really big spreadsheet, I could tell you exactly when any one of the ping pong balls was pulled out. So if we infinitely put ping pong balls in and infinitely keep taking ping pong balls out, the barrel is empty. You cannot name one ping pong ball in the barrel that I cannot name a time when it would have been pulled out. Difficult, I know, to understand, but remember, when we're in this chapter, our brain is using our infinite brain, not our finite brain. So let's stop and take a look now at measuring different sizes of infinity. When you look at this number set, you see the first set is called the natural numbers. 1, 2, 3, 4, 5, 6, and so on. Infinitely many natural numbers. Below are the even numbers. 2, 4, 6, 8, 10, 12, etc. In your mind, are these two sets the same size? Let's think about it. If we look at the bottom set, it appears like half the numbers are there. That would be using a finite set, one with end. But looking at an infinite set, we have to use one-to-one correspondence like 3.1 taught us to do. Is there a way that we can match the top set with the bottom set? Let's take a look. If we draw the lines in red between the numbers, you can see that in fact we do have one-to-one correspondence. In infinite sets, if we have one-to-one correspondence, that means the sets are the same size or have the same cardinality. It is interesting to think what our gut level tells us and what our brain can now learn. In fact, there are two sizes of infinity. The real numbers, which include the rational and the irrational, has a larger set of cardinality than the natural numbers. Think about these decimals. Look carefully towards the end of the infinite decimals. Can you find another number in between? The red number is an example where we changed just one of the digits in the place values, and notice that we found another number in between the two original black numbers. If I line these up and perform one-to-one correspondence with the natural numbers, you can see the first long infinite decimal matches with 1, the red infinite decimal matches with 2, and the third black infinite decimal matches with 3. But look what happens. As soon as we think we have them matched up, you can place another infinite decimal in the middle where you're just changing one digit. You can never keep one-to-one correspondence because you can always insert another real number between the natural numbers. Therefore, the real numbers are larger than the natural numbers. I hope you enjoyed this brain exercise of thinking about infinity and our infinite ways to study and count the different sets. Infinity is the same size for the natural, the rational, the integer, and the whole numbers. However, George Cantor proved for us that the real numbers are a larger size of infinity than the natural numbers. Good luck. Talk to you soon.